Everybody. So it's been a little bit since I've recorded a technical video, just kind of talking about some projects I've done, and I'm a little backlogged on showcasing some of the solar car work I've done. So I'm going through all the different PCBs I've designed in the last 2 years. I'm just going to talk about what I've done on them. And so the first project that I worked on was Buttonboard. So I started Buttonboard in the fall of 2021. So this was the start of my sophomore year, and I was placed on this project as it was designated as a new member project to get a technical person kind of interested in learning about what PCB design. I had no knowledge of any of this beforehand. I didn't even take my first circuits class at this point, so everything was new that I was doing. But we did have two people who were kind of hardware managers or in leadership positions that were helping to explain things to me and walk me through why we were doing what we were doing, and I was kind of just picking up information. So I kind of just wanted to go through and talk about what I've learned with this board, the purpose it serves in the car, and like why we need it. So I'll just kind of go to the PCB viewer here as I talk about like why it's needed. So Buttonboard is what we would call an application board in our solar car, where there will be a communication or interface with the solar car driver so that they can do different things. And with Buttonboard, like you might guess from the name, the job of this board is to get inputs from buttons on the steering wheel for the driver so that they can interface different parts of the car relating to the horn and the light system. So why this is needed is because there's a strict regulation saying you need to have a way to turn on the side turning indicators. You have to be able to turn your horn on whenever you're passing someone at race, or just so you're fit to drive on the road according to the DoD. It also ensures driver safety because of the horn, so they can notify people whenever there's something going wrong. But mostly it's to get inputs from the driver and then transition that through software into outputs and other boards in the car. So applying that. This isn't related to anything power-wise with the battery pack or driving the motors. This is solely focused on driver interfacing and is closely related to another board in the car that I've worked on called horn and lights. So that's kind of why we need it. There's set regulations in the list that we need to follow for ASC and FSGP races. And then they can see, like, as we turn stuff on with the buttons on the steering wheel, they satisfy those conditions. But internally, I would just kind of like to talk about some of the different schematic and circuit choices. So like I said, this was one of the first big projects I did related to electrical engineering and PCB design. So a lot of this was very new to me at first, and looking back on it now, it feels very small and simple, especially compared to other projects I worked on, like our battery protection system. But going through it, I think there's still a lot to learn. You can see there's kind of three main chunks that are divided out in this circuit here. On the top, we have the power section, which is kind of seen all right here. We have the CAN input, which is for our software. And then we have what I just called the input section, which uses pull-down resistors and an RC filter to get rid of noise in the button whenever they're pressed. So a lot of the learning that I did on this board was through the power circuit. And so I technically worked on two different revisions of this board. The first fall that I joined was the first version of it for our P15 solar car, which is Eliana, which we just raced at FSGP, and I have a couple videos of me driving the car on my YouTube channel. But yeah, so then the second version, pretty much everything up in the power circuit stayed the same. The only thing that changed was we added this RC circuit here to get rid of noise in our system and our buttons when they're pressed, so something won't accidentally turn on or off when we don't. So I'll just kind of talk about the power circuit and what I've learned through this. So you can see here J1 is our 12-volt main input. In our solar car, we have three 12-volt lines that are generated from power board, which is a board inside of our battery pack. So we have a 12-volt line that's called 12-volt crit, which is used and powered by a supplemental battery pack. And then basically what it does is it monitors our battery protection system, and once everything's good, we'll start pulling power from our battery pack once we know that it's safe to use. After we start pulling power from our battery pack, that's when 12-volt main turns on, and then all these application boards start to get power. So you can see here on J1, this is our big connector here. It's a 2-pin megafit connector. So we use a lot of megafit and minifit connectors on the car. That's why you can see this package size a little larger than 5-volt input, which I don't even think. Hold on, what I'm thinking of, but I think that was left on there. Anyways, so the 12-volt main source. So we have a MOSFET here, Q2, which acts as reverse polarity protection. So when I was working on this initially, it took me a lot of time to digest MOSFETs and BJTs because I hadn't even taken a intro circuits class just doing math with resistors. Like the pull up and pull down resistors were kind of difficult for me at the time. Looking back on it, it's like, oh, okay, you know, I've had classes on it, I've had experience designing this stuff. Way easier for me now, but it's really fun to look back on and just think about what was challenging then versus what have I taken away from this now. So we have this MOSFET here, which, yeah, we can pull up some stuff in Altium for it. And we use Altium to design all our boards, by the way. So that's what I have running right now. So this is a P-channel MOSFET. And so the way this works is between pins 2 and 3, it will only conduct whenever ground is connected to pin 1, and then whenever a 12-volt line is connected to pin 2. If you swap them, then what'll happen is basically there won't be the correct voltage difference between pin 3 and 1, so that it won't conduct between 3 and 2. So that's kind of how that works. And then after we know that the connector going in is crimped properly and that we don't have the wires mixed up, we have this diode right here, D1, which is just a regular 12-volt TVS diode. Its breakdown voltage is around 14 volts. So if there is a large voltage spike in the car where maybe, let's say, power board fails and right before the Vicor or the regulator dies, it jumps up to 20 volts. Well, when that happens, after it exceeds 15-ish volts on this line, this diode will break down and the current will immediately dump to ground so that none of these parts down the line get damaged, especially this 5-volt switching regulator. These cost us about like $10. And if that happened across all our boards, things start to get expensive when parts are already breaking. So we just add this one diode in here just as a safety feature. This ferrite bead and these capacitors were added in the second revision of the board that I worked on in the spring, the semester after, when we just kind of worked on power filtering and signal filtering. So pretty much what this does is it just couples the voltage and smooths it out going in. This is something we standardize across all our boards at the time. Next up, we have a fuse, which is just a very basic cartridge fuse as seen by F1 right here. We've been moving to a lot more blade fuses because they're easier to tell when they blow, because you'll see the little metal piece in between them will actually disconnect or broken. With these fuse blocks, these block cartridges, you actually have to get a fuse tester or a multimeter to check continuity between the two ends. So it's not very clear. But to make sure it is clear, we added a Fusebond circuit here, which consists of a resistor and LED, the current limit so it doesn't blow up, and then Q1, which is another. And so what this does here is pretty much whenever this fuse blows here, then there is not a connection on pin 1, and then it'll turn this LED on. So this is something so that it's just very easy to tell, hey, you know, is there a connection here? Okay, the fuse blew. There's no connection between pins 1 and 2 of the fuse. So now we want to indicate it visually to the drivers or whoever's in the car debugging it, because if for whatever reason the fuse did blow and we couldn't get power, then we're not going to be able to use our microprocessor to get signals from the buttons and then turn things on in the car like the lights, which is essential and a needed regulation for the race and for driver safety. So after that, we have a pretty standard 5-volt switching reg. You'll notice here that the control line is left open. That's if you just want to keep it powered on. It's just floating. I think somewhere in the data sheet, if you pull it high or low, it can operate. You can either turn it on or off, or it operates in some different state. We just leave it open. Then you have like your input, which is just going to be roughly 12 volts from power board, which is the board and battery pack that generates the 12-volt lines for all the other boards in the car. And then you kind of have this circuit right here. So D2 is just a standard diode. just to protect the switching reg so no current flows back into output pin, so it's always going one direction. And so one interesting thing with this is, you look at the IV characteristics on a diode, roughly that voltage drop is going to be between 0.5 volts to 0.7 volts, depending on the current draw going through the board. Like I said before, the fuse is spec'd at 0.5 amp, so there isn't a ton of current going into this board. Like I said, it's mostly just that RC filter and then pull up, pull down resistors to the microcontroller, so it does not take a lot of current, which is a good thing in our board. We don't want to take too much current for something that's just taking the input of 6 or 7 buttons at once. But what we do to compensate for that, since this voltage drop here would be about 0.5 volt, 0.6 volts, we use a pull-up resistor, and this is listed in the data sheet for the switching reg, which is R-78AA 5.0-1.0 SMDR. You can look this up in the data sheet. We have it in documentation too, talking about how this works. But basically, you just plug in the numbers for the equation on some internal resistors in the circuit, and then you say, hey, I want my output voltage at the Vout node to be, let's say, 5.6 volts. So then after this voltage drop, it'll output 0.5 volts. It took some trial and error, but when I initially did this, one mistake I made was I tried to put the pull up and the pull down resistor at the same time, and that would just over adjust the voltage so it wouldn't actually change. Later on, when I looked back in the data sheet and read it more carefully, I saw that you only need the pull up resistor if you want to make the voltage output larger, which I did, so it could compensate for D2 voltage drop since it's in series. So then here I just have a +5 representing the 5 volt output from the switching regulator that'll be used by the microcontroller and the pull up. And then I also just have a test point. So I think I noticed, I didn't note it over here, but so these little circles are just test points that are little copper pads that you can measure. So those will be generated on the PCB output so that I can measure them with a multimeter in the car, measure them bench testing. And what I do is I actually place vias right beside them so I can actually stick the multimeter probes right inside of that via, so it's easier to press down on and hold, and I'm getting a solid connection. But that's kind of why you'll see these around. And then I also just had a 5 volt indicator LED. This is great for debugging, especially when I was trying to learn how everything worked with like bench testing and multimeters. Because like I said, I started doing this stuff before I took any circuits class, so everything was very new to me at the start, and just having visual indicators is really helpful for people who aren't familiar with the project they're on yet, or just kind of getting comfortable. This is something you could not solder on the board, and people would probably be okay with it. There's also a power indicator on the microcontroller that we use. We have a separate PCB that has a microprocessor on it, and some TVS diodes, and just a general circuit that we can put that board on any of these boards, and you'll see that on the PCB. And that is also what this U2A part is. U2 has several blocks for the microcontroller. If it was all just one giant stack, which it used to be, and it wasn't fun to work with, it's really hard to just put on a schematic page without it taking up the entire thing. But if you don't use a section of it, you can just delete it, which is really nice. But that kind of does it for power. Similar to the actual automotive industry, we use CAN for our software. So I am not software focused on our solar car team technically, but is it normally a general requirement? It is a general requirement that we have two CAN, basically a CAN input and output. It's a bus, so it really just has to go through the board. But so that the microcontroller on this board, right here, and basically it sends CAN into the board, it picks up on what it's saying, and then it goes out. CAN is a bus, so pretty much it can send and receive packets going through here. And that is why we have the CAN high and the CAN low pins connected. This is something we have on each of our boards. There are two CAN lines in our boards, just across the entire electrical system. There is one for the application boards in the front of the car, and then there's one that is only inside of the battery pack, containing power board and our BPS system. And you'll also see here U2B, this is where the CAN line actually goes into the microcontroller. You'll see that it also has that U2 designator like the power above it, which is right up here. So for the inputs, this is kind of the bread and butter of the board. This is why it exists, and it's pretty basic. I added a couple more parts down the line in the second revision, like I mentioned, but the core part of this was just using these pull-up resistors here, connected to this 5-volt line that we generated from the switching reg earlier. So you can see here that I have test points here representing signal lines for the left turn, the right turn, the running lights, the hazards, the bright lights, and the horn. So we have 1, 2, 3, 4, 5, 6 different signals being generated, and I think through the revision that they worked on this year, there was actually 7 pins. But I just used one connector through a 6-pin mini-fit connector J5 here, and then I just kind of put these designators on here, which are net labels, so that you know that line is going to be called left turn, sorry, or horn or hazards, etc. When you're working on that trace in the PCB layout. It's kind of helpful to just have a name for it, since you, hey, this is the signal that software is expecting. But so before we actually get to the software input, something I added on in the spring, kind of near the summer before our track race last year, was this RC circuit, which pretty much is main goal is just to use the capacitors and filter out high frequency noise that could be generated from pressing the buttons up or down when it latches. So we have a combination of latching and non-latching buttons, mostly just due to convenience, because if you think about how you turn on the turn signals in a car, you don't want to have to hold down that button saying, hey, I'm turning, while you're turning the wheel and going. You want to press the button once, let go of it, and then start turning around the wheel. So our turn signals, like our right turn and our left turn, are latching. We also have one of these buttons is being used as a cruise control right now. That is just a press button, and that's just how our software handles setting and disengaging cruise control. Our horn is not latching. It would get very annoying. I can try and find a clip of the horn, but it's loud. If you see my other videos, you know it's loud. So that's not latching, but so there's a variation of them, and either way we want to keep the noise out. I would say it'd probably be more noisy for the non-latching buttons. When you press them up and down really quick, you want to make sure that with that noise it doesn't the software doesn't think that it's getting pressed twice, because then it would engage and disengage cruise control right away, which we don't want that. For something like the horn, that might not be a big deal, but something that does control the state of driving the car, it's very important. And so that was one thing we saw as a priority in the spring. And yeah, so I guess that's about it. Looking at this board after doing a lot of the other work on the car is very interesting and humbling, I guess, because it's really shown how far I've come in understanding circuit design on this level, but also our electrical system as a whole in the solar car, and just knowing different pieces that come in and out of the car and kind of how they work together with this. So it's really interesting. But so then I guess the other part of this that I want to talk about was the PCB design. So this was something new that I also experienced in the first fall of 2021, and it was really cool. I am very happy with how this board went, I guess, is my first one. I joined the team because I was interested in learning PCB design, because if you've seen any of the other projects that I've worked on, you'll probably hear me talk about, oh man, this was really hard to do on a perf board, or oh, these solder joints came out, or oh man, like it's difficult. Looking at what I've done with the LED cube, I just think, man, what if I had a PCB that was 16 holes spread out that I could just solder all those LEDs? You know, it's just everything I've done with a perf board, I've thought, wow, I could do it so much easier now. And I learned how to do all that in this club. It's been a really fun journey, and I've learned a lot in it. But so I guess to kind of talk about the basic layout here is the whole board is highlighted red on the top because this is a 5-volt plane, if I'm not mistaken. And it's a 2-layer board. So yep, the top is that +5 net, which represents 5 volts from the output after the diode regulator. The bottom layer is just main ground, which is the ground that comes into the board, the main ground that's generated from power board. So I'm going to hide both of these so we can see the traces better. So this is kind of the bread and butter of the board. So just to kind of talk about how I organized it and why I did, my main focus was to make sure to have the power circuit kind of in this left column here, so it's very clear when you're working on the board and soldering it, hey, this is that first section of the power circuit, or it's the whole power circuit. It's the first section of the schematic page. So you can see here I have the 12-volt main, megafit input. We have the diode handling reverse polarity protection. You can see that's a pretty small MOSFET. Sorry, not diode. You can see that's a pretty small MOSFET because of the current consumption, because like I said, we're current limited to 0.5 amp through the F1 fuse. So it doesn't need to be a large diode. If there was a larger current draw, it would have to be a larger MOSFET. I'm getting my names up. But the larger MOSFET is seen on some of our other boards when the current consumption is larger, because you don't want this to be the bottleneck for the rest of the board if it does have to draw more current for a reason. If it's like shorting or something like that, we don't want that. But yeah, and then you'll see FB1 and then these 4 capacitors. You can see this is kind of that power smoothing and filtering circuit that we have. Since this is all just M ground, I decided to just make a fill, which is just this block trace here. And so what's interesting is because this is M ground, you will see the outline around it from the 5-volt plane, so that those don't short together and break something on the board. I added a couple different vias spread out between the capacitors. This was definitely overkill for the current that's going through the, you know, from charging and discharging and all that. But you know, it was something I could do easily, and I thought it looked kind of cool. It's fun to do, so I did. And then down here we have the fault LED and R2, which is basically just part of the Fusebond circuit. We have our actual fuse. D1 is that larger PVS diode that we use, so that if the voltage spikes above 14-15 volts, it will dump current into ground. And I guess one thing that I think might be kind of interesting is making this line a little larger, so that if there is that voltage spike, this trace won't burn up going to M ground. But yeah, so then after that we have our switching regulator, which is Q1, and then we have that just regular standard IN4001 diode here, and then you'll see here that this goes into +5. So right here you can see that it goes into this plane, and that is our output current. Like I said, the board shouldn't use more than 0.5 amp, so this via here, it has pretty small traces connected to it, but that's okay because it does not use a lot of current. And then down here you see our 5-volt output, and you can see that's interesting is it's actually just connected to this plane instead of the trace of the diode. And so that kind of shows the benefit starting out of having this whole plane be 5 volts, is I can start using that for a lot of the signal wires. R3 and R1 are that pull-up, pull-down resistor circuit. I think, what is it? R3 is the one that we use, which is a 47K resistor roughly to get about 0.6 volt increase from the output. R1 is just left open, which is why it's listed as DNI, which is just do not implement, do not connect. So that's why I just have a 0 ohm placement resistor there. But just in case we did need to pull a resistor down, there's a pad for it, so we wouldn't need to do a jank or a through-hole resistor somewhere between this pin and like ground. Or it's actually between this pin and the 5-volt line. The other one goes to M ground, that's the pull-up. But yeah, so that's kind of the main power circuit. I will hide this plane again. And so I kind of wanted to keep the resistors and capacitors from the signal line organized, so you can kind of see 3 rows here. All the resistors are 10 kilo ohm resistors, and all the capacitors are 10 UF capacitors. So it's very easy when soldering this, if you've taken a look at the schematic, to say, oh hey, all of these resistors are 10K resistors. If they were spread all out around different signal lines, it might be really confusing to be like, hey, what am I actually looking at here? But if you take a look, it's not too bad. And so I kind of tried to do a vertical signals running down, up and down on the top plane and the top layer of the board, and then I had horizontal signals running to the test points on the bottom side of the board, which are represented by these blue signals. And so you can see over here that these copper pads do come up to the top layer because they're represented in red, and these are just open copper points that you can measure, but then these points are vias that you can use to push your multimeter probes into actually measure. So yeah, that's pretty much it. I mean, I guess kind of it was this was probably the largest challenge I had when I was starting the PCB design, was trying to find the best way to implement 6 different pull-up resistors going into the microcontroller on the same side, because you'll also notice that the CAN line goes to the top of the board too. I didn't make it intentional that we would use only one side. Our software guys are pretty flexible, changing like the pins we use as long as they can take a digital input, which is almost any pin, and as long as we don't use the CAN lines, which are right here beside it, we're good. And we also want to make sure that the different 5-volt and ground lines are connected to the microcontroller, which they are, because all 6 of them are connected with this U2A part that I showed earlier. But yeah, this part definitely gave me the most trouble. Initially on the board, I only had 1 row of these, and then I added that RC circuit, which added pretty much this whole chunk. And I had to get a little more creative then, but by that point, I started working and doing design on other boards. So it wasn't as difficult for me, I guess, to implement it. It still took some thinking, but that critical thinking and thought process is kind of what I enjoy in doing layout changes. The biggest challenge for this was making sure that each of these 5-volt resistors could actually get through this plane and that there were no islands. And so an island is basically when there's a trace encircling everything else. So even if Altium thinks, hey, there's 5 volts here, if this part up here was blocked off, if this part down here was blocked off, there would be no way to actually get that 5 volts from anything. So that's kind of why I did that. But yeah, so I guess that's about it. I've been talking for about 25 minutes now. I'm planning on uploading some other videos covering the Horn and Lights board, which kind of goes hand in hand with this one. For that board, I helped manage it, and I helped lead some new members in the design process, so I'll kind of cover some insights I had on that and our thought processes on why we made changes for that and why it's important for the solar car, especially compared to when the board was at the same time as Buttonboard when I worked on it, because we learned a lot after we put it into the car, and we want to see how can we take that input and these changes and make it better. But yeah, I'm also going to cover some of the work I did on HeadNode, which is one of the boards that we use for our battery protection system. That one is definitely more technical and definitely more in-depth. Not to say this one isn't technical, but there's just a lot more to work with and a lot more to chew on, and I'm pretty proud of the work I've done on it over 2 revisions between the spring of 2022 and then the fall of 2022. No, sorry, spring of 2021, the fall of 2021. But yeah, so it's pretty great. If there's any questions or anything, please feel free to leave a comment. I don't know how much I'm going to edit these. I might just post these as is, brevity. But yeah, I pretty much through the whole process of working on this board, I designed it. I designed the first rev of it for our P15 Solar Car, and designed a second rev to modify it with the filtering circuits. I put together a bill of materials for it. I edited documentation for it. I helped generate the Gerber files for the board order. I soldered the board. I bench tested it. I put it into the car. I tested how it would work with the actual buttons in the car. I was around for a lot of testing processes, so I was able to kind of help debug the board as things went bad in it, or we had problems with our whole electrical system. But it was a really good process. Through this very first process I did in Solar Car, I got the end-to-end development of a printed circuit board, which I never had before. It was a lot of fun. Everyone was super helpful and taught me a lot, and it was really nice being able to teach people and mentor them through that process with our Horn and Lights board. But yeah, thank you. So if you have any questions, let me know. I haven't really done a technical video like this where I sit down with like something up in it, but looking forward to it. I want to try and document all this stuff since I've been working on it nonstop for 2 years. But thank you. Have a good day.